Hello everyone, and welcome to Data Science for Everyone. In this video, we will be exploring supervised learning, a fundamental type of machine learning using the scikit-learn library in Python. This is the first part of a two-part video series. In this video, we will learn the basics of supervised learning and how to use scikit-learn package to perform classification and simple and multiple linear regression. We will also learn about how to evaluate model performance and cross-validation. So, what is machine learning? Machine learning allows computers to make decisions based on data without being explicitly programmed for every task. For example, supervised learning can be used to predict whether an email is a spam or not based on its content and sender. It can also be used in self-driving cars to recognize traffic signals or in image classification tasks like distinguishing between pictures of cats and dogs. Unsupervised learning is the process of discovering hidden patterns or structures in data that hasn't been labeled. For example, a business might want to group its customers into distinct segments based on their purchasing behavior without knowing in advance what those segments should be. This technique is known as clustering, a key method in unsupervised learning. Supervised learning is a type of machine learning where the outcome we want to predict is already known. The goal is to train a model that can accurately predict outcomes for new and unseen data. It works by using explanatory variable or input variables to predict a target or response variable. For example, we might want to predict a basketball player's position based on their points per game. In this case, the points per game is an explanatory variable, and we are going to predict the basketball player's position, which becomes the response variable. In this video, we will focus exclusively on supervised learning. There are two main types of supervised learning: classification and regression. Classification is used to predict the label or category of an observation. For example, using classification, we can predict whether a bank transaction is fraudulent or non-fraudulent. Since there are only two possible outcomes, this is called binary classification. Regression is used to predict continuous numerical variables. For instance, a model using regression can use features like the number of bedrooms or the size of property to predict its price. Before applying supervised learning, certain requirements must be met. The data should have no missing values. All variables or features must be in numeric format. And since we are using scikit-learn in Python, the data should be stored as a pandas data frame or series or as NumPy arrays. One of the great things about scikit-learn is that all supervised learning models follow a consistent syntax. This makes the workflow easy to learn and repeat across different algorithms. Before diving into real-world data, let's get familiar with the general scikit-learn workflow. First, we import a specific model suited for our task from the appropriate sklearn module. Then we create a variable, often called model, and instantiate the selected model class. The model learns patterns on being trained on our explanatory variables x and the response variables y using the .fit method. Finally, we use the predict method to make predictions on a new dataset such as x_new. For instance, if we have a new data that provides the features from 6 emails to a spam classification model, it will return 6 predictions, 1 for spam and 0 for not spam. As mentioned earlier, in this video we will learn how to model classification and regression using scikit-learn and also evaluate model performance and cross-validation. In part 2, we will be learning how to fine-tune models, how one can deal with missing data and categorical data, and how one can evaluate multiple models to choose the right one. Let's begin. Let's build our first model. We'll use an algorithm called k-nearest neighbors or KNN, which is especially popular for classification problems. The core idea behind KNN is simple. To predict the label of a new unlabeled data point, the algorithm looks at the k closest label points and let them vote on that label. For example, If k equals to 3, the model looks at the 3 nearest neighbors. It then uses majority voting to assign the label. The label that appears most often among the neighbors wins. Let's look at the scatter plot. To classify the black data point, if k is equals to 3 and the 2 nearest neighbors are blue, it will be classified as blue. But if k equals to 5 and 3 of those 5 neighbors are red, then the point would be classified as red instead. Let's get started with implementing k nearest neighbors using scikit-learn. First, we will begin by importing our data. We are using the pandas library to load a CSV file called churn_dataset.csv. The link to this data is in the description. Let's take a quick look at the first few rows. As you can see, the dataset contains 3 columns. Monthly charges, which tells us how much a customer pays every month. Tenure, which shows how many months they have been with the company. And churn, which is our target or response variable. 1 means the customer has churned, and 0 means the customer has stayed. In this example, both monthly charges and tenure are our explanatory variables. We'll be using them to predict whether a customer is likely to churn. This is a typical setup for a classification problem, and it's a perfect use of k nearest neighbors or KNN. Let's see how we can use scikit-learn to model it. Now that we have explored the data, let's move on building our k nearest neighbors model using scikit-learn. First, we import the k neighbors classifier from sklearn.neighbors. Next, we define our explanatory and response variables. The variable x contains explanatory variables, that's monthly charges and tenure, and y is our response variable churn, which we are trying to predict. Then we create a KNN classifier object. In this case, we are setting the number of neighbors to 6. This means that the model will look at 6 nearest data points to decide whether a new customer is likely to churn or not. Finally, we fit the model to our data using the fit method. This trains the classifier using our dataset. And that's it. With just few lines of code, our model is ready to make predictions. Now that our model is trained, let's see it in action by making some predictions. We start by importing NumPy. Here, we have created a new NumPy array called new data. Each row in this array represents a new customer with their monthly charges and tenure. So for example, the first customer is paying $85.50 and has been with the company for 12 months, and so on and so forth. We'll pass this data into our trained KNN model to predict whether each customer is likely to churn or stay. Let's run those predictions next. Now it's time to make our predictions. We use the predict method from our trained KNN model and pass the new data array we just created. This gives us a prediction for each new customer. We then print the results. Here's what we get: 0, 0, and 1. This means that the first 2 customers are predicted not to churn, they're labeled as 0. The third customer, however, is predicted to churn, they're labeled as 1. So based on our model, customers with higher monthly charges and shorter tenure might be at more risk of leaving. This is how simple and powerful KNN can be for classification tasks using scikit-learn. Now that we can make predictions using a classifier, how do we know if those predictions are actually correct? We need to evaluate the model's performance. In classification tasks, one of the most commonly used metrics is accuracy. Accuracy is calculated as number of correct predictions divided by the total number of observations. You might think to measure accuracy on the same data that you use to train the model. But there's a problem. Since the model has already seen this data, the accuracy will likely be overly optimistic. What we really care about is how well the model performs on unseen data, because that's what tells us how well it can generalize in real-world scenarios. To evaluate the model properly, it's a common practice to split the data into 2 parts, a training set and a test set. We use the training set to fit the classifier. That's where the model learns. Then we test the model by calculating its accuracy on the test set, using the true labels to see how well the model performs on unseen data. This approach gives us a better estimate of how the model will perform in real scenarios. To split our data, we import train test split from scikit-learn.model selection. Then we call the train test split passing our features, that is x, and our target, that is y. It is common to reserve 20 to 30% of the data for testing. In this case, we set test_size argument to 0.3 to use 30% of the data as a test set. We also set the random state argument, which controls the random splitting process, and using the same value ensures we get the same split every time we run it. To make sure that the class proportions are preserved in both sets, for example, if only 10% of the observations represent churn, we set stratify equals to y. The train test split returns 4 arrays: xtrain, xtest, the training and testing features, and ytrain and ytest, the training and testing labels. Next, we instantiate a KNN model and fit it using the .fit method. To evaluate the model's accuracy, we call the .score method, which returns the accuracy. In this example, our model achieves 71% accuracy. Let's discuss on model complexity and how to interpret K. Recall that we discussed decision boundaries, which are thresholds for determining what label a model assigns to an observation. Simpler models are less able to detect these relationships in dataset, which leads to something known as underfitting. In contrast, complex models can be sensitive to noise in the training data, rather than reflecting general trends. This is known as overfitting. We can better understand the impact of K by visualizing a model complexity curve. With a KNN model, we can calculate the training and test accuracies across a range of K values and plot the results. Here's the general workflow. Initialize 2 empty dictionaries to store the training and test accuracies. Then create an array with a range of K values to test. For each of the value of K in the array, instantiate a KNN model with n_neighbors equals to K. Fit the model to the training data, and then calculate accuracy on both the training and the test set. Store these accuracy values in the appropriate dictionary. This process helps us to visualize how model performance changes as we increase or decrease the model complexity by varying K, thus helping us choose a good balance between underfitting and overfitting. We then plot the training and the test values using matplotlib. The result is shown in the right. We see that as K increases beyond 22, we see underfitting, where the performance plateaus on both the test and the training sets. The peak test accuracy actually occurs around 20 neighbors. This brings to an end of how we can perform classification using the scikit-learn library. In the next few slides, we will look at regression, which is a second type of supervised learning. Recall that classification is used on binary data, whereas regression is used on continuous data. If you liked this video, please like, subscribe, and comment. It really motivates me to make more videos like this. Thank you. Let's start with the concepts of regression. I'm going to go over the main concepts of regression in this video. I have made 2 other videos in this channel explaining regression in detail, along with how to perform regression in R and Python. Please check them out. I have provided links in the video description. Now let's look at a general modeling formula. In this formula, y is a function of x. Y is called the response variable, and x is called an explanatory variable. Y is a variable that you want to model, and x is a variable that you use to predict the values of y. F denotes a mathematical function that defines a relationship between y and x. F of x is called the signal. E or epsilon is called the noise, that represents the error in the model. In a perfect model, E or the error becomes 0. This is the most important concept in modeling. A good model has high signal-to-noise ratio. In regression tasks, the response variable typically has continuous values such as a country's GDP or, for example, the price of a house. Let's take a real-world example to understand regression problems better. I have a data set with health information for women, and our goal is to predict their blood glucose levels. We'll start by loading the dataset into a pandas data frame and taking a quick look at the first few rows. By the way, the data is linked in the description below. The dataset includes several health-related features, things like the number of pregnancies, insulin levels, BMI or body mass index, age, and whether or not the person has been diagnosed with diabetes as an outcome variable. A value of 1 means they have diabetes, and a value of 0 means they don't. In scikit-learn, we need to separate our data into two parts, one for the explanatory variable and one for the target we want to predict, which is also called the response variable. These are usually stored in variables named x and y. So here's what I've done. I have dropped the column for blood glucose levels, since that's what we are trying to predict, and used the rest of the dataset as our input features, which I have stored in x. Then I have stored the actual blood glucose values in a separate variable called y. The values of x and y are stored in numpy arrays, just the format scikit-learn expects. Let's start simple. We will try to predict the blood glucose levels using just one feature or one explanatory variable called the body mass index or BMI. To do that, we grab the BMI column from our input data. It's the fourth column, and we will store that in a new variable called x_BMI. When we check the shapes of x_BMI and y, we see that they are both a one-dimensional array. That's fine for y, but scikit-learn expects that our explanatory variable to be in a two-dimensional format. To fix this, we reshape x_BMI using numpy. We call the reshape method with -1 and 1, which tells numpy to figure out the right number of rows and make it a single column. After reshaping, we print the shape again, and we will see that x_BMI is now in the correct format for training our model. Now let's visualize the relationship between BMI and blood glucose levels. We'll start by importing matplotlib.pyplot as plot, and then create a scatter plot by passing x_BMI and y to plot.scatter. To make the plot easier to read, we'll add labels to the axis using plot.xlabel and plot.ylabel functions. Looking at the plot, we can see a general trend. As BMI increases, blood glucose levels tend to rise as well. Now it's time to fit a regression model to our data. We're going to use linear regression, which fits a straight line to the data points. First, we import linear regression from sklearn.linearModel and then create an instance for the model. Since we are modeling the relationship between BMI and blood glucose levels, we will train the model on all the data we have. We do that by calling reg.fit and passing our explanatory variables and response variables just like we did with the classification models. Once the model is trained, we can make the predictions by calling reg.predict method and passing our explanatory variable. Since we are predicting on the same data we used to train our model, this gives us a line of best fit. To visualize, we recreate our scatter plot of the original data and then use plt.plot function to draw the predicted line, passing in x_BMI and the predicted values. The red line shows linear regression model's fit, predicting blood glucose levels based on the BMI of the individual. From the plot, we can see a weak to moderate positive correlation. As BMI increases, blood glucose levels tend to go up as well. In the last example, we performed simple linear regression, where there is one explanatory and one response variable. Now I'm going to demonstrate how to perform multiple linear regression, where we will be using multiple explanatory variables. when we have two explanatory variables, say x1 and x2, the equation for the linear model changes to y equals to m1 times x1 plus m2 times x2 plus c, where m1 and m2 are coefficients for each explanatory variable and c is the intercept. When we add more features, this becomes what's called multiple linear regression. In this case, we need a separate coefficients for each explanatory variable plus an intercept c. To fit a multiple linear regression model in scikit-learn, we'll use just two variables, one for the explanatory variable called x and one for the response variable called y. Scikit-learn handles the rest under the hood. Let's take a look. Let's perform linear regression to predict blood glucose levels using all the other variables in the diabetes dataset. First, we import linear regression from scikitlearn.linearModel and also bring in the train test split to split our data. We separate the explanatory variable and the response variable. We drop the glucose column from the dataset and store the rest of the columns as our explanatory variable dataset called x, and keep just the glucose column as the response variable as y. Next, we split the data into training and test sets using the 70-30 training and test ratio. The train test split returns four arrays: xtrain and xtest, the training and testing features, and ytrain and ytest are the training and testing responses. Next, we instantiate a regression model as reg_full and fit it using the .fit method. Finally, we make predictions on the test set. It's worth noting that scikit-learn's linear regression performs ordinary least squares or OLS behind the scenes. Finally, we print out a couple of predicted values alongside the actual ones, and as you can see, the model does a reasonable job in estimating blood glucose levels. In the next few slides, we'll look at how to evaluate model performance using several metrics such as r-squared, mean squared error, and root mean squared error. In linear regression, the default metric we use to measure performance is called r-squared, which is also called coefficient of determination. It tells us how much of the variation in the target variable, what we are trying to predict, is explained by the explanatory variables. R-squared values range from 0 to 1. A value of 1 means the features or the explanatory variables perfectly explain the target variable's behavior, while 0 means they explain none of it. To calculate r-squared, we use the model's .score method, giving it the explanatory variables and the actual response variables as arguments. In this example, the model returns an r-squared of 0.285, which means the explanatory variables explain only about 28.5% of the variation in blood glucose levels. Another way to measure how well a regression model is doing is by looking at the mean squared error, or MSE. This is the average of the squared differences between the predicted values and the actual values. These are also called residuals. Mean squared error, or MSE, is measured in the square of the response variable's units. So if we are predicting something like, say, meters, the mean squared error will be meters squared. To bring it back to the original units, we take the square root of the MSE. This gives us the root mean squared error, or RMSE, which is easier to interpret because it is in the same unit as the response variable. To calculate MSE and RMSE, we start by importing mean squared error and root mean squared error functions from scikitlearn.metrics. Then we call it by passing ytest, which are the true values, and ypred, the predicted values. Looking at the root mean squared error, we see that the model has an average error of about 25 milligrams per deciliter when predicting blood glucose levels. With that, we come to the final part of this video where we will learn cross-validation. If you liked this video, please like, subscribe, and comment. It really motivates me to make more videos like this. Thank you. So why do we need cross-validation? When we compute r-squared on our test set, it depends on how we split the data. if the test set happens to have some unusual data points, the R-squared we get might not accurately reflect the model's true ability to predict new and unseen data. To address this and avoid any biases from the random splitting, we use a technique called cross-validation. This method helps ensure that our model's performance is more reliable and representative of how it will perform on any new data. To perform cross-validation, we start by splitting the dataset into several equal groups or folds. Here we're splitting the data into 5 equal folds. First, we set aside the first fold as a test set and then train our model on the 4 other folds. After making the predictions on the test set, we calculate the metric we're interested in, let's say R-squared. Next, we repeat the process with the second fold as a test set, training on the remaining 4 other folds. Likewise, we do the same for the third, fourth, and fifth folds. At the end, we'll have 5 different R-squared values. From these, we can calculate useful statistics like mean and median to get more reliable measure on how our model is likely to perform on new and unseen data. Since we are splitting the data into 5 folds, it is called 5-fold cross-validation. If we split the data into 6 folds, it would be called 6-fold cross-validation. In general, if we split the data into k folds, it is called k-fold cross-validation. However, there's a trade-off. The more folds we use, the more computationally expensive the process becomes. This is because we need to fit and predict the model more times, which takes up time and resources. To perform k-fold cross-validation in scikit-learn, we begin by importing cross-val score from sklearn.model selection. We also import k-fold, which helps us control how the data is split. We start by setting up a k-fold object. By default, it splits the data into 5 folds, but you can use whatever you want using the n-splits argument. We also set the shuffle equals to true to shuffle the data before splitting it into folds, ensuring a more random and representative split. To make our results repeatable, we assigned a seed to random state argument, so every time we run this, the data will be split in the same way. We save this setup as the variable k-fold. Next, we instantiate our model, in this case linear regression. We then call cross-val score, passing the model, the explanatory data, and the response data as the first 3 arguments. We specify the number of folds by setting the CV argument to our k-fold variable. This returns an array of cross-validation scores, which we store in CV scores. The length of this array corresponds to the number of folds we have used. By default, the R-squared score is reported, as it is the standard metric for linear regression. Finally, to get a better understanding of how our model is performing, we can calculate the mean score using np.mean and the standard deviation with np.standard functions. We can also calculate the 95% confidence interval for our results using the np.quantile function. To do this, we pass our CV results and specify a list of the upper and lower bounds of the interval, represented as decimals, 0.025 for the lower bound and 0.075 for the upper bound. With that, we come to an end of how we can use scikit-learn to model classification and regression tasks in Python. In the next video, we'll be learning how to fine-tune models, how one can deal with missing data and categorical data, and how one can evaluate multiple models to choose the right one. If you liked this video, please like, subscribe, and comment. It really motivates me to make more videos like this. Thank you.